last very interesting topic that I would like to discuss while we are hovering on this topic of hard disk is the problem of scheduling. There are many research articles and a lot of invention went behind in research and engineering went behind the topic of scheduling and mastering the scheduling while dealing with hard disks. So what is scheduling? In particularly here we are talking about the disk scheduling. What is disk scheduling? And why do we need it? Because of the high cost of I/O, as we saw that I/O is not something to be considered for free, right? We have a lot of I/O time that includes seek time, rotation time, and the transfer time. And because that's high, OS has historically played a role in deciding the order of IOs issued to the disk. And this process of deciding the order is called scheduling. Which IO should be scheduled first, or which IO should be scheduled second, third, so on and so forth, right? We are scheduling the IOs, the order in which IOs needs to be issued to the disk. That's what is called scheduling. Now, given a set of IO requests, disk schedulers examines all requests and decides that which one to schedule next. Sounds like a very simple job, right? Where you have a bunch of IOs, just look at this bunch of IOs and decide which IO should go next, right? Is it that simple? Put one more thought to that idea. Well, not that simple, but still we could, I'm sure you could think of some ideas depending. Once you have a bunch of IOs, you would want to put the IOs that are in the consecutive sectors, issue them one after the other, right? That could be one trick. You want to issue maybe smaller IOs first because you know it would take smaller time. Maybe you have some idea of where the disk head is located at this moment. So maybe then you want to issue the IOs that are near to that disk head's location, so that we don't have to perform additional seek and additional rotation to move the disk head. So yes, these are definitely some very valuable ideas in like maybe 20 to 30 years back would have resulted into a research paper. But we have already much advanced field of scheduling today, so it wouldn't work as it is. Maybe you have to come up with even better ideas in today's world. But one good thing is, unlike job scheduling, here in disk scheduling, we can guess or approximate, right? How long will each IO take? Because how can we approximate this? because we know the average IO rate of that disk. Once you know the average IO rate, you know, depending if you know the average read rate or average write rate, then we know that approximately depending on IO size, we can always find out how much time that particular IO would take, right? IO write rate, the equation itself is equal to IO size divided by time. So if you know IO rate, if you know size, then definitely you could calculate the time that it would take. And this one thing, like just having that approximation of how much time it would take makes a lot of things in the scheduling much easier than job scheduling. Now, looking at some of the popular scheduling schemes. The first and the most simplest disk scheduling algorithm is first come, first served. It's basically do nothing, right? In the order in which IOs are coming, just issue them as it is to the disk. Now, this scheduling technique, first come, first served, is reasonable because we don't have to do any additional work for that. When load is low, so we wouldn't mind the additional T-seek and T-rotate that we would get for each T-transfer for the time to how much time that we are spending towards each IO, then that's fine. If we anyway have very few IOs to be done, doesn't matter how much time we spend towards that. So it's reasonable when load is low, but long waiting times for long request queue is the biggest disadvantage. Because if you already have many jobs which arrived before you and are not yet completed, then probably that IO needs to wait for much more longer time, right? It just came at a wrong time. It's something like when there is a hurricane warning in Miami, and then you go to a gas station, either you would find that it's out of gas, or you would find there is a huge queue of cars in front of that gas station that has gas. Probably that's the first come first served algorithm that the gas station is using, right? The car that comes first can fill the gas first, and then the remaining all gets queued in that line. So you don't want to end up being at the gas station during just before the hurricane alert. Otherwise, on a normal days, being at the gas station anytime is pretty much fine, right? There are many gas pumps. If not one, the other would be empty, and you could just fill your gas right there at one of it. The second popular scheduling technique is shortest seek time first or nearest block first. Shortest seek time first or nearest block first. This again, as you would have anticipated, that if we don't want to spend much time in seeking from all the way from one track to the track at the other end, then probably it's a good idea to schedule the IOs that are in nearby tracks at the same time, or that are in nearby blocks at the same time, nearby sectors at the same time, so that you don't have to spend time in rotating if you schedule the IOs on a nearby sectors on the same track. And if we schedule the IOs on nearby track, then we spend less time in seeking. Now, these two policies are intuitive with a reason that we are minimizing arm movements, such as seek time and rotation time. And we are rotation time for nearest block first, near shortest seek time first, seek time. And we are maximizing request serving rate, because we could serve more IOs in a short period of time because we waste less time in seeking and rotating. Now, these both are the advantages of this scheme, but is there any disadvantage of these schemes? Would it favor few particular blocks or tracks more over few others? Think a bit. Yes, there is obviously a disadvantage. Most of the things in systems have two sides, like two sides of the coin, right? So if there is advantage, there is probably a disadvantage. It depends on the scenario. So it depends could be an answer to many things in systems while we are talking about operating systems or storage systems. But whenever I ask you any questions, if we meet when we meet in person or in some of my office hours, then I hope you don't reply to each of my question as it depends, because I could ask you for, let's say that we are having a conversation and then we have this thing where I bring up that, okay, we are done with an exam for this course, so let's go out for a coffee, or maybe we submitted a research article together, so let's celebrate, let's go out for a coffee. And then if you would just reply by default, it depends, upon saying that it depends if you would join or not, well, not that fit to that situation, right? So use it depends in the domain of storage systems, operating systems, but use it wisely and do ensure that you know the reason why it depends behind that. Coming back to SSTF and DF, the disadvantage of that is it favors middle blocks or tracks. Because in a disk, once your head comes to any middle track, blocks are just consecutively numbered across sectors from track to track, going from outside to inside. But once you come into that center range, then because you have one track above, one track below, it's high likely that you would be just serving those tracks and blocks in that center range, neglecting the ones in the outer track and neglecting those outer tracks, as well as neglecting the innermost tracks. So it's not fair. And sometimes in extreme case, this could lead to the problem of starvation. It could happen that the request on the outer track is starved, that it's never served even after waiting for long time. Because it's just that there is another request that comes at the last moment, and that's in one of those tracks that lies before that outermost track. So that's given priority over that request that arrived long back, but it's in the outermost track. Now, to solve this problem of starvation, people came up with, or people invented, this is our third, right? Yeah. people invented a new scheduling technique called scan. What scan does is it sweep back and forth across the tracks. Thus, if the request comes on the track that was already served in this sweep, then that's queued for next sweep. So what happens in scan is, let's say we are on this, the head is on this track in the center, and because as the definition says, we are sweeping back and forth, and let's say we are sweeping, basically we're sweeping inside and outside. So let's say in this, at this time we were sweeping outside, so we completed serving the request within this, all the inside tracks. We are here and we are further going on to serve the IOs that further lies in the outside tracks, such as this one. And at that time we get another request that is on a track just inwards to that, or maybe we just completed serving this track and we get a request that's on the same track. But rather than giving priority to serving one of these, we would still keep on sweeping to our next track in the direction. So the head would be moved to this track and we would serve all the IOs that arrived on this track. And then so on and so forth, we would go all the way towards the lastmost track, and then we would start our journey back inside. So then we would complete all the IOs that were then in the meantime scheduled in the intermediate tracks. So this is the process of scan. Now, with this concept, we definitely solve the problem of starvation. Nobody starves, right? Because all the tracks get an equal attention. But it could happen that if we, depending on where our starting position is, if we are starting from inside, then the outermost track is getting consecutive attention in the two so we would go all the way from inside to outside, and then we would start our journey back inside. So the time in which we would get to serve the request on the outermost track would definitely be larger compared to the time in which we are serving the request on one of these tracks in between, because we are touching them twice, right? Once while going and once while coming back. While the innermost and outermost, we are just touching them once. So people invented different variants of scan. One of the popular variant is C-scan, where again, a very basic intuitive idea that rather than going all the way from inside to outside and then inside to outside and then outside to inside, let's just do circular scan. So only one direction, C stands for circular, so only one direction sweep. It's more fair to the outer tracks than scan. So rather than doing in this way, we are doing only one direction sweep. So we would move from inside to outside, then we would move the head all the way back to inside and then start sweeping from inside to outside. Now, alike to these scan and C-scan, we have a couple other algorithms such as look and CLOOK. Even they are very popular, the scheduling algorithms. So what is look and CLOOK? They are like scan and C-scan, but only goes as far as last requests in each direction. Well, it's just again one more step, right? Another smart idea upon scan and C-scan. What this idea is inspired by is that while we are seeking from insidemost track to the outsidemost track, if the last IO request that we received is right on the track 4, and let's say in total we have 15 tracks, then, but if there is no request that's outstanding yet between track 4 and track 15, what's the point of going all the way until track 15, right? You might better as well serve the other requests that are within track 0 and track 4. So a small very logical step, but lead it to a very performance improving scheduling algorithm. And so on and so forth. There are many other scheduling algorithms that are inspired by such basic intuitive ideas like shortest job first, shortest positioning time first, which would require which is a bit more detailed, which requires like more hard disk specific details on predicting the time from going from one location to the other, and then issuing an IO that has the least positioning time from the current location to the position of wherever we want to perform the IO. But again, if it requires the details from hard disk, then such algorithms like shortest positioning time first is not a good place to do in operating system, because operating system would not have all the inside details of hard disk. As we saw already, that we do prefer to use a generic IO stack, and we want operating system to just have an abstraction of how to access a device and not exactly all the intricacies and worry about the details of exactly how data is stored on which cylinder, on which plate, on which surface, and all these many details. So again, feel free to dig more into other scheduling algorithms and do spend some thoughts on if you were at this job of designing a better version of existing scheduling algorithms or designing even a new scheduling algorithm, what changes would you make and why would you make those changes? And who knows, maybe you would come up with a better inspired from these existing algorithms, you would get some idea that would solve our problems for emerging devices such as flash-based storage and all the new evolving technologies of storage systems. Well, best luck inventing and thinking about these new ideas. You know my email. If you would like to discuss any cool ideas, then shoot me an email or show up in my office hours, and it would be my pleasure to discuss those ideas and thoughts with you to brainstorm them. That's it. Thank you. Bye-bye.